Hi everyone. In this video, we will begin an overview of some preliminary concepts that will be important to our understanding of all of the theorems to follow. I encourage you to approach this video with an open mind because it's easy to look at this and say these are all things that I already understand and know about. In fact, in this video, we are primarily going to be discussing functions. But hopefully, as you'll see by the end of the video, not everything is as straightforward as it sometimes seems. And so we want to make sure that we are all on the same page and have a common understanding of the notion of a function and some related definitions before we move forward. So the first question one might ask is, well, what is a function? If you ask a lot of just say calculus students what a function is, they may give you something like this. Right? F of x is equal to x squared, a nice quadratic, simple quadratic function. And this is sort of a perfectly reasonable notion for them to have, but we start to notice that it is actually rather imprecise. We have not specified here what the domain of this function is. So, for example, it is possible that I mean this for x in say the natural numbers. My marker's dying a little bit there. So possible that I mean this for x being a natural number, right? In which case, I'm really only defining this function at the values 1, 2, 3, 4, 5, 6, 7, 8, and so on. But perhaps instead, right, I mean, for any real valued x. Now, commonly, we would say in a calculus course, well, if you see this relationship here and we're defining it as a function, then we're going to define it as a function for the largest subset of the real numbers for which the right-hand side is defined. Well, this right-hand side, x squared, is defined for every real value of x. So we would sort of commonly just assume that the domain of this function was all real numbers, and therefore this would be a well-defined function. But we start to notice that, okay, this is a function defined by an equation, and even here there are some ambiguities. We, of course, do not have to have an algebraic expression that defines a function. There are many other ways to define functions between things. So, for example, there is a function from each student's name to their Appalachian State banner ID number, right? And that function just takes as an input your name and spits out as an output your banner ID number, which is a specific format of number, right? It's not easy to write in this notation what that function would be, even though conceptually we can think of it. Okay? So what we tend to do then is take a more abstract notion in defining a function. So a function f, for our purposes, is a set of ordered pairs such that no two different pairs have the same first coordinate. The set of first coordinates is called the domain of f, and the set of second coordinates is called the range of f. So back to our previous example, I had f of x is equal to x squared, and if I wanted to take x to be all my real numbers, right, I could express this as a set of ordered pairs. The first entry is x, the second entry is x squared, and I want to do this for each real number x. Okay? That is, of course, a distinct function from, say, the set of ordered pairs 1, 1, and 4, 16, even though you will note that the y-coordinate of each of these ordered pairs, or the second coordinate of each of these ordered pairs, is just the square of the first coordinate. There's the same relationship between the x and y coordinates here. However, they have different domains. Here, the domain, the set of all first coordinates, is all real numbers. Here, the set of all first coordinates is just the singleton 1 and the singleton 4, right? So they have very different domains, even though there's the same relationship between the x and y coordinates. This defines a relationship between the first and the second coordinates, but tells us nothing about the domain. So having this more abstract notion of a function can be helpful when trying to understand some certain properties of the behavior of function that have to do with its domain, as opposed to just the relationship between the x and the y coordinate. Now, we can certainly apply functions to particular numbers, right? So back to my example, f of x is equal to x squared, then f of 2 is 4. But we may also want to apply functions to subsets of their domain, right? So if we have a function f which maps from some set x to some set y, and A is a subset of the domain and B is a subset of the codomain y, then we can define these two additional sets. This set here is actually what we would refer to as the image of A. Okay, so that first set is the image of A. This second set here would be the pre-image of B. Okay, so these do have names. They are the image of A and the pre-image of B. And to see what they're doing, let's think about this a little bit visually. So you can imagine I have here some set X, and I have over here some set Y, and I have a function that maps things from X into Y. And now imagine that I have sitting inside here some subset A. Okay. Now, I could look and ask myself, well, what happens if I take all of the things that are in A and look at where they end up over here? Where do they go? Well, that's precisely what the image of A, or f of A, is. It's the set of all things that if I map everything in A over here, I know it's going to land somewhere in Y. If I look at all the things that get hit in Y by mapping elements of from the set A, then that gives me what's called f of A. Now, the preimage does sort of the reverse. So the preimage says, well, let's look at some set sitting over here, say B, in the codomain, and let's look at all the things over here in X that when you map them end up in B. So over here, I might have F inverse of B, and these are all the things that end up getting mapped over into B here. Okay. So we can talk about the image or the pre-image of a particular set. Once we have a function, we can look at the image of some subset of the domain or the pre-image of some subset of the codomain. Now, often these can feel very abstract. The kind of picture I have just drawn can be very helpful when you're trying to think about these notions. And I encourage you to try and replicate such a picture on your own, maybe after watching this. All right. Additionally, we want to remind ourselves of some properties of functions. You've likely seen these, encountered these before elsewhere in the math curriculum. So there are sort of two notions. There's the notion of a function being injective, which we also sometimes refer to as being one-to-one. And there's the notion of a function being surjective, which we also refer to as being onto. So going back to our kind of diagram from before, if I have some set X, some set Y, my function f, which is mapping in between them. A function is injective if the only way that f of x1, or sorry, if when f of x1 is equal to f of x2, that means that x1 must be equal to x2. Said another way, a function is injective, or one-to-one, if the only way you get the same outputs is to have the same inputs. So for example, if I were to look over here and see, aha, look, I put some value in here, x1, and I put a value in here, x2, and they actually came back to the same point. Well, the only way that could have happened is for x1 and x2 to be the same over here. What you cannot have happen for an injective function is for these to have come from different places. This cannot happen for an injective function. You can't have two distinct points in the domain mapping to the same output. For surjectivity, or onto, okay, you see the definition written there. So it says for each y in y, there is an x in x with f of x equal to y. Said slightly more simply, what that means is every y value over here in my codomain is hit by some point x which maps over to y. So pick any y you want, then there's some x here that maps to that. And pick any y you want, there's some x here which maps to that. Pick any y you want, there's some x here that maps to that. And you can always find, for every y over here, you can find a value of x so that f of x maps to y. Okay, so said a slightly different way, this really means that the image of your domain, f of capital, this is capital X, the image of your domain is equal to your codomain. So if you map your whole domain, then you have to end up hitting everything over here. Okay. Now, you'll notice I've spent a lot of time sort of talking about injectivity and surjectivity, but there's this third term, which is to be bijective or bijectivity. That simply means that you're both injective and surjective. Now, the reason these properties are important, and we may explore this more in an exercise set, is that if a function is both injective and surjective, we can very easily talk about its inverse function. So if f is both injective and surjective, so bijective, then we can think about if we have a function from x to y, we naturally have an inverse function which maps from y back into x. So injectivity and surjectivity are both very helpful properties when we want to talk about inverse functions. And on their own, they're also important for other types of discussions we'll have about theorems later on. Now, with those definitions in mind, I want us to spend a little time thinking through some questions. And what I'm going to encourage you to do is to consider each question, pause the video, and then let's talk a little bit more in depth after you've paused it and had some time to think about it. We'll talk a little bit more about the problem and what's going on. So the first question is, are the functions f of x is equal to sine of x plus cosine of x and g of z is equal to cosine of z plus sine of z the same or different functions? So if you're watching this, pause your video, think about this for a minute, particularly think about it in relation to the definition of a function, and see what you come up with. All right, now that we're back together, let's take a look at the first question. It turns out that, first of all, this question is a bit ill-defined. So I've given you some relationships here. So I've given you f of x is equal to sine of x plus cosine of x, and g of z is equal to cosine of z plus sine of z, but I haven't given you a domain. So you could sort of complain that, well, I don't really know what the function is because you haven't given me a domain. But as we said before, typically when we see these sorts of things, we choose the domain, if it's not otherwise specified, to be the largest subset of the real numbers on which these are defined. Well, if I look at sine of x plus cosine of x, let's see. Well, sine of x is defined for every real value of x. Cosine of x is defined for every real value of x. And then I'm just adding together two real numbers, so that's fine. So the domain of the first relationship is, of the right-hand side, is all real numbers. Similarly, down here, right, for every real value of z, cosine of z is defined. For every real value of z, sine of z is defined, and then I can add them together. So the domain of that is all real numbers. So if I think about this, I need to think about the function as a set of ordered pairs. Now, commonly, a Calc 1 student might tell you, well, these are different functions. I mean, they have different variables. They have, this one's name is G and this one's name is F. So they might tell you, well, these are just different functions because they have different variables and different names. But knowing what we know about the definition of a function, we can actually see that these functions are the same. And why are they the same? They're the same because they give us the same sets of ordered pairs. So if I think about the function f, okay, and I think about it as a set of ordered pairs, f is giving me the set of all x, comma, sine of x plus cosine of x, such that x is a real number. Okay. The function g is giving me the set of all points z, comma, cosine of z plus sine of z, such that z is a real number. Now, as sets, these two sets are equal because they contain exactly the same elements. If you wanted to write a very formal proof of this, what you could do is you would show that f is a subset of g. So that is, show that every ordered pair that lies in F also lies in G. Then you would show that G is a subset of F. That is, show that every ordered pair in G lies in F. And those would combine to imply that F and G are equal as sets. And if they're equal as sets, then they have to be the same function because functions are just sets of ordered pairs. To have some idea of how, say, this, you might prove this, right? If you want to show f is a subset of g, you take something in something in f. So for a fixed x value, this point is in my set f. So there's an arbitrary thing in my set f. And then I'm going to show that it is also in G. And the way I'm going to do that is I'm going to say, well, pick your z value to be equal to x. So choose z is equal to x. And then you have that x comma cosine x plus sine of x is in G, right? Because I'm just putting in x for my z value, and that's okay because x is a real number, and this works for any real value of z. So I'm going to plug this in here, but then I notice that this is in fact just the same thing by the fact that addition is commutative as x comma sine of x plus cosine of x. So this also has to be in G. To prove the other way around, you basically start here and work your way up here. Okay, so now this is this is a very sort of abstract way of thinking about this, but it's a way that helps us sort of rigorously define what we mean by function. It doesn't matter truly what you call the variable. The variable is just sort of a placeholder. What matters are the ordered pairs that you can generate from these functions. All right, now let's move on to our second question. So are the functions f of x is equal to x squared minus 4 over x minus 2 and g of x is equal to x plus 2 the same function or different functions? So again, if you're watching this, pause the video, take some time to think it over. And once you've had a chance to think it over, hit play again and we'll discuss this more in depth. All right, great. So let's examine these two functions. So if I look at f of x, I have f of x is x squared minus 4 over x minus 2, and I have g of x is equal to x plus 2. Okay. Now, again here, the first thing we might want to think about, because it's not specified, is what are the domains of these functions? Well, let's actually start with g of x because that's fairly straightforward. I can plug in any real value of x here and add 2 to it. That's something I can always do, right? So here, my domain, and by the way, we'll sometimes abbreviate domain this way. This is the set of all real numbers. What about this function up top? Well, if I look at this up top, I'm going to have a problem here when my denominator is equal to 0. So when my denominator is equal to 0, which is when x is equal to 2, this expression on the right will be undefined. So my domain here, oh, and I wrote the wrong ones down here. Sorry, this should be the domain of G. My domain of F will be all numbers except 2. So all the numbers from minus infinity to 2, union with all the numbers from 2 to infinity. But notice that neither of these, 2 is not included at either endpoint. So this is like all the real numbers except I'm sort of plucking out the number 2. Now, as soon as we know that our domains are not equal to each other, then these can't possibly be the same function. Okay. Now, again, commonly a calculus student would tell you that these are the same because they would say, well, x squared minus 4 over x minus 2. I can factor the top. This factors as x minus 2, x plus 2 over x minus 2. I will cancel the x minus 2's, and I'll be left with x plus 2, and aha, look, these are the same. Now, of course, what has happened is this cancellation, right, is only valid when x is not equal to 2. So what you actually proven here is that these things are equal when x is not equal to 2. When x is not equal to 2, yes, these things are equal to each other. But when x is equal to 2, these are not equal to each other because when x is equal to 2, this is defined, but this is not. Now, the fact that these two functions are equal at every point except at 2 is actually very important. And it allows us to do a lot of important things when it comes to, for example, calculating limits, as we'll see later this week. However, as functions, these are different functions. And so when we swap them out, we have to actually be careful about the fact that these are in fact different functions. They just happen to be equal in almost every place. Now, finally, we have time for sort of one more problem, and this will be sort of our first proof of the course. I thought it might be nice to just remind ourselves of how we go about proving some things. So what I want us to try and prove is that if I take the image of A intersect B, then that is a subset of f of A intersect f of B. Now, before I set you off to maybe try this on your own, let's sort of remember a couple of things definitionally first. Okay, so we're going to assume here that A and B are both subsets of the domain of F. Okay, and then what we're going to do here is we want to show that if I take something in here, then it must also live in here. Okay. Now, this, again, this is where drawing pictures can help. Okay, so here's my set X, here's my domain, here's my range. Okay. Let's assume I have sort of some set A here and some set B here. Okay. Now, what I want to show, if I were to take A intersect B, That would be the little striped portion in the middle here, right? So A intersect B is where they overlap. And then I could look at where that maps to. I could also look at where A maps to and where B maps to. So visually, sort of what I'm doing here is if I can imagine over here, maybe this is like f of A. Maybe I have another thing that's like f of B. And what I want to show are that if I take something in here, okay, that it ends up mapping somewhere in here because this piece sitting right here at the intersection, maybe this piece here is actually f of A intersect f of B. Okay. So try to think through this, and then we'll write down, like, think about why this ought to be true, right? Why, if I take something in the intersection of A and B and map it over here, why does it have to end up in the intersection of f of A and f of B? So pause the video, take some time to think through this, and then when you come back, we'll write out a nice proof. All right, great. Let's look at how we would formally prove this. So anytime I want to prove that some set is a subset of another set, so I have some set here, I want to prove that it is a subset of this other set. The way I'm going to do this is I'm going to start by taking an arbitrary thing over here, okay? So I am, for example, going to I'm just going to give a name to my thing. So I'm going to let A be in f of A intersect B. Okay. And sorry, actually, I don't want to call this X. I'm going to call this Y. The reason I'm going to call this Y is that this thing lives right in the range, right? It's something that's already been mapped. It's f of something. All right. So let Y be something in f of A intersect B. Well, the first thing I'm going to do is just write out what does that mean? Well, if Y lives in f of A intersect B, then that means there exists an X in A intersect B such that f of X is equal to Y. So really what I'm saying here is since Y is in f of A intersect B, there's got to be some X in A intersect B that maps to that Y. Okay. Well, let's see, then what can we do with that? Well, I know this X is in A intersect B, which means what? If X is in A intersect B, that means it's in A and it's in B. Okay, so then X is in A and X is in B. All right, well, let's work first with the fact that X is in A. If X is in A, then f of X is in f of A. Right? That makes sense because if X is in A, well, f of A are just all the things that get hit by mapping something out of A over into Y. So if X is in A, f of X has to be in f of A. But what is f of X? F of X is just Y. The Y is in f of A. Okay. Similarly, let's do the same thing with B. So since X is in B, f of X, which is just equal to Y, is in f of B. So now Y is both in f of B and it's in f of A. Hence, Y has to be in f of A intersect f of B, because f of A intersect f of B are just all the things that are both in f of a and f of b. So now what have we done? We've started with something arbitrary in f of a intersect b, and we've shown that if you take anything in f of a intersect b, that has to be in f of a intersect f of b. So we've now shown that anything that lives in this set must also live in this set, and therefore this set is a subset of this set. Now, I'm going to give you a general piece of advice here which will apply throughout the entire semester. So even if I don't repeat it every time, I think this is true. What you want to try and do when you first see a proof is you want to make sure you can sort of follow it through. Do I understand logically like why this implies the next step? So for example, do I understand why if y is in f of a intersect b, then there must be an x in a intersect b such that f of x intercepts y. So you sort of understand it line by line. And why does this line imply this line? And why does this line imply this line? So on and so on. Then you want to go back through and sort of try to understand it more broadly, right? This is sort of the why question. Okay, I understand that this implies this, but why does that work? And why do we want to do it in the course of this proof that we're looking at? Okay. Now, once you make it through all those steps and you feel like, okay, I finally am starting to understand this proof, what you often want to do then is put it away. And maybe come back to this problem in a day or two and see if on your own you could recreate this proof. Understanding proofs and becoming a better proof writer is an iterative process, and nobody does it by themselves. So what I encourage you to do is to try to reach out to me when you need help, either a quick question I can answer by email, or if you want to set up an appointment to talk about it further. And then work towards that sort of independent understanding and mastery where eventually you're able to reproduce these sorts of proofs on your own. That concludes this video on sort of some of the preliminary notions of a function. In the next video, we'll begin talking about limits and reminding ourselves of why limits were important for calculus and how we went about calculating them.